49 people, so I'm hitting go live on YouTube. And now I would like to officially welcome everyone to this new online seminar series, Radiation Belts in. So I'm hitting go. How do we prevent feedback? And now I would like to officially welcome. My bad. I'm sorry. I didn't realize that I shouldn't have myself playing on YouTube while I'm talking on YouTube. In any case, welcome all to RBSP, which stands for Radiation Belts in Space Physics, and to anyone who might be new to our online seminars, that the history and the origins of these seminars go back at least a decade, or if not more than that, prior to the launch of Van Allen probes, Van Allen radiation belt storm probes. And RBSP, of course, was the acronym that we were known by before it was renamed at the launch. We are, of course, you know, it's been a decade, and we held this telecons first with just members of the teams, and then opened it up very quickly after the launch to the scientific community at large, that encouraged participation from anywhere in the world. And we fostered and really witnessed an entire vibrant community being developed over the course of these 10 years. And of course, the scope of the interest of this community grew far beyond original goals of the Van Allen probes mission, and the community, of course, spans a much broader group of people than just those associated with the mission itself. So we would like this new revived seminar series, which we're going to hold monthly, roughly monthly, to reflect both of these facts. So to that end, the topic of the first seminar will bring us all the way to Jupiter, and we're going to hear two outstanding talks on various aspects of the exploration of most intense radiation belts as we know them in planetary magnetospheres in the solar system. And of course, just a quick note before we give the floor to our speakers is that we also have a number of organizers, and the organizers also span the entire international community now, not just in the United States here, but we have our colleagues from Europe and Japan, who we're very proud to have with us organizing this series. And I already said it before we went live, but to repeat it very quickly, the way we're going to run it, this is going to be as informal as we can have in the group of 70 plus people who are joining us, is that both of our speakers will take quick questions and for clarification while they're giving their talks, but there will be no questions after they complete their talks. Instead, we're going to wait until the end of the second talk, and then we'll open up for questions and discussion, and any free remarks that we have within this hour. And very quickly, something that I forgot to mention, that at the bottom of this webpage, that is our new webpage for the seminar series, which we're going to advertise in the SPA newsletters. You see not just our names, but our email addresses. So if you think of something or you would like to propose a topic for one of these upcoming seminars / conversations, please let us know. It's always completely open, and we would love to have a broad discussion on what are the most important things that folks in this community are working on. All right, and with that, I'm going to give the floor to our first speaker, George Clark from APL, who is going to announce his talk himself. And I will stop sharing.
Okay, thank you, Sasha, very much. Just a quick
While
check.
George is sharing, please make sure that everybody else but George mute their mics.
Okay, and Sasha, you can see and hear me? That's all great?
Yeah.
Okay,
yes.
Perfect, thank you. Yeah, I am very grateful that you gave me the chance to discuss some of the discoveries from the Juno mission, as well as this really exciting COMPASS mission concept, which was recently funded by NASA to support the Solar and Space Physics Decadal Survey. So the title of the talk is Particle Origins, Acceleration, and Losses in the Extremes of Jupiter's Giant Magnetosphere. And so with this talk, I'm going to kind of frame some of the discoveries around these three main themes. Of course, there's so much more that the Juno mission is providing us right now, and we have a limited amount of time. So I am always happy to field questions through email or whatever after, if you'd like to learn more about the mission and its impact on outer planetary physics, space physics. Okay. So like I said, we'll talk about a brief background of the Jovian system, namely its configuration, the dynamics, and the radiation belts. We'll also talk about fundamental mysteries of Jupiter's magnetosphere and the radiation belts, in particular the particle origins, acceleration processes, loss processes, and emphasis on new discoveries from NASA's Juno mission. And I'm just realizing that I spelled out pale. That's not at all what I'm trying to get across. Okay. We also will talk about the NASA heliophysics mission concept, and then we'll summarize the presentation. And like Sasha said, this is informal. Please interrupt and ask me questions along the way. And if I have to, I can speed up certain sections to make sure we stick to the time allotted. Right, so first off, Jupiter has this immensely large magnetosphere. And on this plot here, it just provides a sense of scale where Earth's magnetosphere kind of is encompassed by something a little bit larger than Jupiter itself. And so you can see how much larger Jupiter's magnetosphere is in the bubble that it carves out in the solar wind. At first glance, you'll see a lot of similar types of configurations that you would at Earth, with the magnetosheath, the magnetopause, a bow shock. You have a current sheet, and then, in a tail system as well. But then you also have deep inside the inner magnetosphere, a plasma torus that is sourced by the neutrals coming off of Io that are then ionized and picked up in the magnetic field. And so that's kind of one thing that's probably a striking difference from the Earth system. And we'll talk more about that. Jupiter also has many, many moons, but I'm going to just highlight some of the Galilean moons to note. So Io, of course, as we know, is geologically active with volcanoes. And through its surface and atmospheric interactions with the magnetosphere, it supplies Jupiter's magnetosphere with sulfur and oxygen, primarily from dissociation and ionization from sulfur dioxide. Europa is also a moon that is of high scientific interest in the planetary community. It's thought to have plumes that supply water products nearby and form a neutral torus, and also a plasma torus of like H2O, and O2. Recent work by Todd Smith, I think, really nailed that down. And there's also been supporting information from like UBS instruments and such like that. Ganymede is interesting because it's not only the largest moon, but it also has a strong internal magnetic field, strong enough to stand off the magnetic and thermal pressures of the Jovian system. So it forms this mini magnetosphere, and it also has a tenuous atmosphere. And of course, there's Callisto, has a potential subsurface ocean with a tenuous atmosphere, and maybe a very weak source of neutrals and plasma, but it's unknown at the moment. Um, so these moons are embedded kind of in the inner and middle magnetosphere of Jupiter. And as a consequence, their roles in supplying the plasma in that region really has a large impact on Jupiter's magnetospheric configuration. The neutrals that are ionized are picked up by the magnetic field, and so the mass loads the system. And as the magnetic field lines rotate at the footprint of the planet at the rotational speed, there's a lot of stresses with that newly added mass in the equatorial magnetosphere. As a consequence of those of that process, there's the topology of the magnetic field, which is shown here on the right-hand side. You can see that there is a bend back feature and also a current system that is set up to help communicate the torque that is needed to kind of keep things up at rigid co-rotation. Now, the inset here in this plot just kind of shows the dynamics of like kind of the inner region with the radiation belts that goes with the rotation of the planet, that being because its magnetic moment is offset from its rotation axis. There's a host of processes that add to the dynamics of Jupiter's magnetosphere, which are thought to be driven largely by internal forcing. You have a leakage of particles along the boundary of the magnetosphere. Barry Mock has recently published things that show how particles can leak easily when they're on order of the gyro radius is on order of the thickness of that boundary. You have injection events that might mimic something like storm type events on an Earth's magnetosphere. You also have particle burst. So these were observed by rapid changes in the anisotropy of the ion distributions that occur kind of in the outer magnetosphere. And then you also have interchange events too, which is a process deep in the inner magnetosphere, kind of near Io and outward. Interchange is thought to be more of like a centrifugal driven process where you have the rapid rotation and you have basically essentially the gravity force with different density plasmas, and then you have interchanging of flux tubes that bring hot tenuous plasma in from the outer magnetosphere in exchange with the colder dense plasma in the inner magnetosphere. The injection events and dipolarizations are kind of these rapid onset processes that transfer large amounts of particles inward that then gradient curvature drift and become energized. There's thought to be a quasi-periodic or a quasi-period associated with these processes. In the top right-hand corner, you'll see that Vogt et al. In 1998 wrote about these kind of 2-day loading and 1-day unloading process associated with the dipolarizations and injections in Jupiter's magnetosphere. Jupiter also has very intense radiation belts. So on the left-hand side of this plot, which was provided by Quintin Ninan based off 2 of his papers, on the left-hand side, you can see that the belt structure here is composed of hundreds of keV electrons up to 50 to 70 MeV. We don't quite know where that upper limit is. On the right-hand side, you can see the protons and heavy ions from hundreds of keV up to greater than 10 GeV. And you can kind of see their structure as well as they interact with various absorbers and wave processes throughout the middle magnetosphere, which we'll talk about shortly. Just wanted to add context for those that know Earth much better. On the bottom left-hand side shows a plot of Earth radiation belts and kind of their more temporal and spatial structure, and also provides some energies as well in the outer and inner belts. And you can see that Jupiter is orders of magnitude more energetic and also seems to lack kind of that temporal and spatial variability that is seen on Earth. And then the inset plot here showing the electron spectra as a function of energy just kind of reinforces that idea that Jupiter's electron belt anyways goes up to much, much larger energies and larger intensities. So as a consequence of that very energetic electron radiation belt in the inner magnetosphere, Jupiter has synchrotron emissions. And these have been observed primarily from Earth-based assets, but also some radars on board like Cassini and stuff, and Juno with its MWR. But these emissions here kind of put it in class with astrophysical systems that also emit synchrotron. And these emissions are modulated with the rotation of Jupiter. So kind of talked briefly about some various highlights, very briefly about some highlights in the Jupiter system. And now I kind of want to transition from the background to kind of the fundamental mysteries of Jupiter's magnetosphere and radiation belts. So here's that same graphic from the Quinton Ninon simulations, but now we've annotated it with the processes that we know, but are unsure of the role and how they transport and accelerate particles throughout the magnetosphere, and also some regions where we just have guesses of things that may be going on. So the rest of the talk here is to kind of frame some of the new discoveries from the Juno and even the Galileo mission, and then talk about how we might address these with the future mission concept. For what it's worth, the color code here is the pink is associated with sources and acceleration, and the blue lines are associated with loss processes. And you can see that there's different processes depending on the species of the plasma, meaning electrons or the ions. So we believe that there's three key pieces to understanding Jupiter's magnetosphere and radiation belts, and that is the origins, so the creation of the charged particles and other high energy sources, the acceleration processes, meaning the transport and energization to relativistic energies, and losses, which are critical in controlling the dynamics of the radiation belts and other factors in the magnetosphere. So we'll first talk a little bit about some Galileo and Juno discoveries. So one in particular that I would like to highlight came from a reanalysis of the Galileo heavy ion counter data by Elias Roussos, just published early this year. So they found evidence for a energetic oxygen source inside of Almathea, which is roughly inside of like 2.5 RJ. They found that so over here on the left is a phase-space density profile for constant mu's as a function of M shell. M shell is what we refer to in Jupiter as being the equatorial crossing distance of a given field line. So these phase-space density profiles, and especially if you look at the kind of the blue and the red, you see that in the inner magnetosphere, you see rising phase-space densities. And what's also interesting is if you look at the pitch angle plots of the greater than 50 MeV per nuc oxygen, you see that in that same region, this is right here in 2.5 M shell, that you now have intensities or rates peaking near 90 degrees. What's interesting about that is near 90-degree pitch angle, you'd also assume that's where the more significant losses would occur. So kind of the pitch angle picture and also the phase-space density picture tells you or provides pretty strong evidence that there's likely a source of very energetic greater than 50 MeV per nuc oxygen in this region. It's thought that this is likely due to either low frequency heating from low frequency waves, or possibly nuclear processes such as spallation, which is ejection of heavy ions from dust materials and stuff like that. So this quote from Elias here just says, this puts Jupiter's ion radiation belt in the same league with the astrophysical particle accelerators. And I just wanted to highlight that sentence. I really liked it. So I want to now talk about auroral acceleration processes and as a source of hundreds of keV to MeV ions and electrons. Sasha, could you butt in and tell me when you want me to wrap up in like 2 or 3 minutes, please, just so I can make sure I get everything in.
We have a few minutes, George. So
okay,
that's okay.
Okay, I think maybe I'll speed up a little bit. So auroral, we're finding with Juno that there's definitely no shortage of energetic particles being created over the polar region. We find that in the polar cap region of Jupiter, electron inverted Vs that accelerate electrons up and outward away from the planet to hundreds of keV is a pretty routine signature. Barry Mock has published results showing that even in the main auroral region, the upward energy fluxes associated with the electrons, auroral accelerations with the electrons, often exceeds that of the downward region, and enough intensity to even populate some of the higher energies of the radiation belts. We also find that ions are routinely supplied via outflow up to hundreds of keV. And of course, signature processes with the moons, and I won't talk about this much, but we also see that there's hundreds of keV ions, especially associated with Io's footprint tail, that are being transported away from that region and fill the inner magnetosphere. So if we look at transport, I want to highlight this here on the left that shows kind of some measurements from the Galileo mission with some possible questions here as well. Peter Coleman has showed that the cutoff energy in the measured energetic particle distributions matches well with adiabatic or radial transport, so conservation of adiabatic invariance. And you can see inside of like 15 RJ that the blue deviates strongly from the orange curve. There's many things that could be going on here. If you look at the green curve, we see that there's a peak in the chorus intensity. But we also know that Galileo struggled with making clean measurements of the energetic particles in this region. So understanding if this is a representative profile or if really local sources are starting to take over is something that we just don't know at the moment. On the right-hand side, we know that, that there's a finer structure associated with radiation belts as seen from like Earth with the so-called zebra stripes. At Jupiter, simulations show that the above a 1 MeV, we expect similar types of structures. However, current instrumentation with the Juno JEDI only covers a fairly limited range when you think about the whole range of the radiation belts. So we're kind of blind to that region. And this is important for understanding kind of like magnetospheric electric fields and their role in the acceleration and transport of particles. Precipitation is also a key loss mechanism. Wen Li has shown that the diffuse aurora is likely a result from Whistler mode waves scattering the electrons into the loss cone. Work done by Chris Paranikis and Quinton have shown that ion depletions near the vicinity of Io, but also much larger than Io itself, are likely the consequence of EMIC waves being scattered into the atmosphere at that location. Sorry for not going into details in these plots, and then Jamie Soleil has shown also that associated with Io, alphanic turbulence and Whistler mode waves also cause a large amount of precipitation near the moon footprints. So with those slides, I just kind of wanted to highlight some of the new discoveries and the open questions that we have with Juno and the Galileo, and then talk a little bit about COMPASS, which is going to go after the origins, acceleration, and loss processes associated with some of these. So COMPASS stands for Comprehensive Observations of Magnetospheric Particle Acceleration Sources and Sinks. It's a STP class mission concept, and the goal really is to help prepare for the next solar and space physics decadal survey by offering a cross-disciplinary concept that kind of expands the frontiers of heliophysics by exploring the radiation belts of other systems. We have this unprecedented scientific payload to measure the in situ fields and particles associated with the radiation belt processes at Jupiter. And we have a payload that can do energy resolved measurements greater than 1 MeV for electron and ion populations, which is absolutely key, as I showed earlier, in understanding some of those physical processes. We're also excited because we're going to carry an X-ray imager, and that X-ray imager is going to do a lot for monitoring the dynamics of the radiation belts and other processes, and also the loss processes. And you can think of it much like what ENAs are doing for global context. We can do that with X-rays at Jupiter. Okay, this will be the last or second to last slide here. So the COMPASS mission concept, the whole idea is that we need to get unprecedented coverage inside of Io and down inside of 1.6 RJ, where the synchrotron emission region is. And so we have an orbit that actually does that with this COMPASS concept. You can see here in the left in this YX GSE plane that COMPASS has a roughly 17-month tour. And we'll make several passes inside of Io, and we go down, I believe, to between 1.5 and 1.6 RJ. On the right-hand side, we have two phases in the mission. One really targeting the X-ray observations near closest approach. So we have a high latitude part, and then the purple shown by the green curves, and this is magnetic latitude as distance, and then the purple curves show that we have this kind of unprecedented coverage inside of Io all the way down to roughly 1.6 RJ at magnetic latitudes near zero. That's really going to help us understand these processes and likely unlock new discoveries, or make new discoveries rather. Yeah, we'll take we have a plan to basically take in situ survey data that meets the science requirements, but we will also take burst data. We know how important, from like Van Allen probes, for example, how important burst data is in understanding these physical processes and leading to new discoveries. And so we have a plan to acquire that data, and also a plan to downlink a subset of that. All right, I will put the summary up. So essentially, Jupiter offers this unique magnetospheric laboratory to test our ideas on the origins, acceleration, and loss processes associated with extreme environments. We know that Jupiter is ripe for discovery. NASA's Juno mission has shown us that already, but it's also paving the way for new, exciting questions to be explored. And the COMPASS mission is really a community-wide mission that it was developed to kind of go after those new questions, and also to test some of the theories that have been developed at Earth with great missions like Van Allen probes and SAMPEX and CRUST. All right, Sasha, I'm all done. Thank you very much.
Thank you, George. And as I mentioned, we'll table some questions and discussion to the end of the seminar. I just wanted to quickly add that for those folks who are not as deeply engaged with COMPASS as you are, that you have been incredibly modest, and George here is the PI of this concept study.
Thank you.
Many folks on this Zoom call also participate in it.
Yes.
And this is an ongoing study, and we will all be able to read about it when this study is published, way before the actual decadal survey. So if you stop sharing now, thank you, George.
Yes, I'd be happy to.
We will give the floor to Bing Zhang, who is joining us all the way from Hong Kong University. And I, again, very, very much appreciate that Bing stayed up late. He's 12 time zones ahead of us. So he's almost in the weekend. All right, Bing, please take us away.
All right, okay, I'm gonna share my, can you guys hear me?
I can see your face, which is good, but not the talk yet.
Okay, so let me share my screen. Let's see, where is it? There we go. Can you see my screen now?
That's perfect.
This one, okay. And you can see my cursor too, right?
Yes.
Okay. So I'm gonna talk about some of the modeling work that we did to look at the what the magnetosphere of the Jupiter looked like in general, and we found something quite interesting, and we call it unusual compared to what our basic knowledge about the Earth is. And this is from a global image simulation from the code Gamera, developed mostly by APL colleagues. And also, this is a long list of my collaborators, and especially Peter Dalamir from University of Alaska, who convinced me that the simulation results is probably right. So that's exciting. And since another reason Jupiter is my favorite planet now is that because I'm working mostly in the geology department. So I with my colleagues that, you know, there's no continent, there's no tectonics, so you can't find a job in Jupiter. It's only me. So that leads to what they think what I'm working as a space scientist is they call me space geology, either me walking on the moon of Jupiter, or I'm working with a geology hammer trying to dig into the surface of Jupiter, what's look like. All right, so, okay, I'm gonna go back to the real work. So what I'm going to talk about is that we're looking at a magnetosphere, how magnetospheres form by interacting with the solar wind and the planetary magnetic field. So the basic fundamental model is called a Dungy magnetosphere. So if you remember the Dungy magnetosphere, magnetic field lines are opened on the day side and closed on the night side, form this closed field lines and open polar cap. with surrounded by the aurora morphology like this. So if we try to apply this Danzi magnetosphere to the Jupiter model, and what would you expect aurora to be look like? This is Earth, right? So you would expect something look like this because this region is mostly open. So that leads to the motivation of our study, why this is so different. So there are two figures. One is the Juno UVS image of the aurora morphology in the northern polar region of the Jupiter. And this is the Earth image, WIC image from the aurora oval. So you can see that the Earth model follows more or less about Danzi magnetosphere, and it's dark polar cap, which means that's mostly open field lines. While the Jovian model is slightly different, I'm calling this region is the oval of the aurora, and then there are lots of emissions in the polar region that's not like what the Danzi magnetosphere that you'd expect, right? So what the question is, what are these polar emissions coming from? And there's also what do they mean? They mean that the magnetosphere must be different compared to what the Earth is look like, right? So we use the global simulation, which is the Gamera code developed mostly at the APL. And we adapted the Earth model to be a Jupiter. So first couple of things, that Gamera is a MHD solver that solves the MHD equation on non-orthogonal grid. It has a very high resolving power and very low numerical diffusion. And then we can apply that to different scales, different problems. So we design a grid of the Jovian magnetosphere, which is huge, crosses about 1,000 Jovian radii in the tail and about 800 Jovian radii in the dawn dusk north-south directions. And the difference between the Jovian magnetosphere and the Earth is that the solar wind is much weaker with a lower magnitude of the IMF, and two terms. One is the planet rotates about 10 hours per spin, and also we need to add the Eoplasma torus because that introduces about 500 kilograms per second to about 2,000 kilograms per second mass to the systems. That's the main source of the Jovian magnetosphere plasma. So we simulate this system for a long time until we get a radio density profile. It's about steady state. So this is what the simulation looks like. So it looks like Earth, right? So we're looking down the northern hemisphere. This is where the Jupiter is, and this is the plasma torus and disk. And then you're looking at the density down here, and also this is the magnetic field of the Z components. So you can see that there are lots of instabilities, and the magnetosphere is very dynamic. It looks like Earth, but it's actually not that much, right? So one thing to look at is how good the simulation is doing. We look at the density profiles from the simulation. So this is a direct comparison of all the density profile from the different local times. So the stars are from the simulation, and then the rest of them are data from Fran and Peter's paper. And this is the mass per meter along the radial direction, and compare with the simulation with the empirical relations. So we can say that with this kind of resolution and the model, and then we are capturing the magnetodisk relatively well. Right. So now we are doing this relatively well, and then we're looking at how much open flux can the solar wind generate through the interaction. So we're looking at the Dayside interaction is that when the solar wind reconnects with the planetary magnetic field, there's a reconnection electric field along the separatrix. So if we integrate the electric field from the reconnection along the separatrix, and we can estimate the amount of open flux from the Faraday's law by calculating two parameters. One is the reconnection potential along the separatrix on the day side, and the other one is how long is that reconnection potential imposed onto the system. So to calculate these two terms, and we dig into the simulation data, and we're looking at the average B field. So this is the magnetic field topology average over one spin. So we're trying to identify where the reconnection is happening, and we integrate the electric field along these separatrix, and together reconnection potential is about 500 kilovolts. And that's consistent with observations, estimations based on observations. So how long does that potential is imposed to the system? We use another simple way to look at the time difference between the first flux tube reconnected down here and the last flux tube reconnect back in the tail. So that distance about 279 Jovian radii, and based on the speed, it's about 48,000 seconds. Right? So based on these two parameters, we estimate the open flux to about 24 gig Weber. Right? So think about this, Earth is about 1 gig Weber. So you think that this is like 24 times larger than the Earth. So it's pretty large, but remember that the Jovian planetary size is 10 times larger in radii, and also the magnetic field is 20 times larger. So if you look at this, and that's basically what 24 gig Weber open flux should look like. So that's the aurora and the subpolar aurora, and that's a tiny region that's with the 24 gig Weber open flux, right? So if the open flux is that small, which means most of the region it's closed. So how should this be distributed over the polar cap? And then we look into the code and we trace the location of the field lines from the ionosphere. So we're showing that the green, this is this is an altitude shell of the simulation shell of the magnetosphere, and this region, and then the green region is the region where the field lines are connected to the IMF, and everywhere else is closed, which means the northern hemisphere connected to the southern hemisphere. So you can see that how is the 28 gig Weber redistributed over the polar cap. It's forming a crescent shaped rather than a circular shape like a Dayside magnetosphere. It has a large dawn-dusk asymmetry, and with more flux distributed over the dusk side, over the, oh no, this is the dawn side of the magnetosphere. And there's also an interesting region that very close to the pole, and we call this a patch region, and we'll show you what that field lines will look like. So this is a simulated Jovian magnetosphere and open flux region. And if we compare this with the simple aurora image, and you can see that I changed this to be, this is noon, this is midnight, this is dawn, dusk. So the same orientation of this, my simulation plot. And you can kind of see that this dark region, which is called a dark polar region in the Jovian aurora, and you can see that it forms more or less this kind of half moon shaped region with dark without emission. And you can possibly imagine that's possibly a region connected to the solar wind, but we definitely need more data to verify this. Okay, so this open flux region looks very smooth and nice, but it actually varies a lot with time. So this is an animation showing you that, is it playing? Showing you that the variation of the open flux region over one planetary spin. So the green region is open, everywhere else is closed, and then the color is showing the field line currents, and red is upward currents, and gray is downward currents. So you can see that the open region X actually rotates with the planets, and it's very dynamic over one planetary spin. So these are snapshots of the open region. So you can see that the crescent-shaped region changes with time. Also, the patch region near the pole also varies a lot, and they're actually very more dramatically than the crescent-shaped region, and because they disappear for half of the time. So this is also showing you that the system is extremely dynamic, and it's not as simple as just a completely open polar cap from a Dayside magnetosphere. Right? So the question is, if the polar cap is closed without connecting to the solar wind, how's the field topology look like? So we trace the field lines from the Jovian magnetosphere. So this circle is actually the 6RJ, is the 6RJ boundary in this simulation, not the size of the Jupiter. Jupiter is much smaller. So we trace the three sets of field lines from 80 degrees in the latitude and 82 degrees, 80 degrees, and also the open region, green ones, and also the patch region where it is above 85 degrees. So you see three sets of field lines, and the first one is the 80-degree ones. They're mostly closed, but they're twisted. And the green ones are connected to the IMF because we're using BY as the IMF. So they're mostly connected to the IMF to the dusk side. And also the interesting region is that the patch region, which is very close to the pole, and they're actually circulating around. and really dragged back down to the tail. And there's another circle we did here with the black circle, which is above the open field lines, higher out latitude than this. And you can see that these black flux tubes come out from the northern hemisphere and connect to the southern hemisphere through the dawn side. And this is because these field lines are the reconnection, dayside reconnection is not fast enough. So it cannot open all the flux tubes on the dayside. So those flux tubes coming out from the northern hemisphere, they cannot be reconnected. So they just rotate and connect through the southern hemisphere from the dawn side flank. And this forms a very complicated geometry of the Jovian magnetic field. And you can see that this is a very different structure compared to our knowledge of the Danji cycle magnetosphere. So the particles, you will have, this is a giant reservoir of particles and electromagnetic wave energies to power all these things. But we don't have any new results at the moment. So if you look at the three-dimensional view of the magnetic field structure, and this is basically the topology rotating. It's the same figure, but it's rotating with time. And you can see that these are the field lines connecting, and this is the distant tail, and this stretches down all the way to 1,000 Jovian radii can extend all the way to the Saturn orbit. And the black curves are from the pole, but they're connecting to the southern hemisphere through the dawn side flanks. So that's a very unique structure that we don't see in the Earth magnetosphere, and that definitely requires more study and validations. So to this point, and we want to understand why this is generating this kind of feature. So we're trying to think of a question, how do we generate this for other planetary stuff? So the hypothesis is that morphology of these open polar cap changes with the spin. So why is that? Is because there's two controlling factors. One is how fast flux tubes are open, and the other one is how fast is the rotation speed. So we define two potentials. One is the merging potential, which is basically reconnection potential determined by the planetary and also the IMF, and the other one's co-rotation potential. And we define one parameter called R phi, is basically the ratio between the reconnection potential and co-rotation potential. So that's the equation. And if for Earth, it's much larger than 1, and for Jupiter, it's much smaller than 1. Right? So we did a bunch of numerical experiments, say if we spin the Earth faster, we can actually transit the Earth from the Earth to the Jupiter. So we did this crazy set of numerical experiments called this. So these are the parameters of the Earth, and pay attention to the rotation speed. Everything else is nominal, solar wind conditions and others. And when we spin up the Earth by decreasing the rotation period by a factor of 7 to 100, and we can actually decrease the ratio down from about 11 and to about 0.1, and that's very close to the ratio, the parameter at Jupiter, and Saturn is somewhere in between. And this is an interesting numerical experiment using Earth as a test bed. And the criticize I got from my collaborators is that if we spin the Earth faster than 20 times than now, and it will just explode. But that's a geology problem. We're not considered with that. Right. So let's take a look at when we increase the rotation speed. And you can see that from baseline, the Danji magnetosphere is mostly open. And if we spin this up, and you can kind of see this structure of the spiraling of the open flux, and eventually we transit from the Earth, from the Danji magnetosphere to the Jovian magnetosphere. So this black curve is the open-closed boundary, and you can kind of see this. So we transit from Earth to Jupiter based on our simple one-dimensional parameter study down there. So how does the field topology look like? So the comparison between these simulations actually tells us a lot. And if you can see that this is the baseline Danji magnetosphere of the Earth, and the polar cap is mostly open, and that's the field line from 85 degrees. And when we increase the spin, and some of these lobes actually spin towards the dawn side, and they cannot get reconnected with the solar wind, and then they start to become closed. So as the spin gets faster and faster, and this pile up region, because of the faster spin over the reconnection, they actually increased a lot and eventually become something look like the Jovian Magnetosphere, right? So compared to this, and we can kind of see that Earth is right here, and Jupiter is more like this, and Saturn is somewhere in between, can be either one depending on the driving conditions. So if you look at the percentage open of the polar cap, and we look at the open polar cap above 80 degrees magnetic latitude, and you can see that the Earth is mostly open, about almost 100% open for nominal driving conditions. And the Jupiter is about 20% open. So most of the Jovian magnetosphere is closed above 80 degrees, while Saturn can be either of any of these cases. So we're trying to look at the aurora morphologies if we think that the aurora morphology tells us a little bit about what the topology should look like. And this is Earth, which is mostly open, and this is Jupiter that's closed. And these two are from the Saturn, and just to pick two examples quickly by my collaborator. And you can see that Saturn could be either look like Earth and was like mostly open, and also like half of the polar cap is populated by these intense emissions, which looks like somewhere in between. Right, so that's an interesting numerical experiments telling us that it's controlled by the topology, is controlled by the rotation and also the Dayside merging as well. So when we consider the global geometry of the magnetosphere, and we need to consider a parameter like this before we look at the details. So to summarize, for what we did from the numerical experiments is that if you look at the Jovian magnetosphere for nominal solar wind IMF conditions, and the polar cap is mostly closed. And from our simulation, if you use a nominal driving conditions, about 9% of polar cap is open above 82 degrees. And which means that the open polar cap does not follow the classic Dungey picture. And that's something we know for a while, and has been debating in the community as well. So this is influenced by the planetary rotation. And the shape and openness of the polar magnetosphere is determined by the ratio between the merging potential and the co-rotation potential. And of course, other facts such as mass loading, maybe ionospheres are also important. And we definitely need more observations to validate the model. And which I think the most interesting part is that if the polar cap is completely open between the two, closed between the two hemispheres, it's a large region with all these particle energization, particle populations, and also the acceleration and then can happen other than just an open polar cap like a Dungey magnetosphere. So this is basically all I have, and that's all. Thanks.
Thank you very much. There is one question in the chat, which I'm sure you already read and know how to answer. No, I'm kidding. Of course, question from Robin Millen. Why don't you ask it, Robin, so we don't put pressure on Ben?
Sure. Can you hear me?
Yes.
Okay. Hi, Ben. Thank you both for great talks. I was just wondering, and maybe this gets to your last point, if you could use the synchrotron emission and the radio observations to constrain. It seems like if you have those black field lines you were showing, there would be an asymmetry in the radio emission. And I know for many years they've fit the beaming curve of Jupiter to pull out information about the magnetic topology, and wondering if you could do that to test this model.
So I'm not sure if I understand your question exactly. So one is you're saying that these field topologies are detectable through the radio emissions?
Yeah. So I mean, I don't know if it's that far out. I mean, so the synchrotron emission, like George was showing, is really strong because the field is so strong and the particle energies are so high in the inner magnetosphere. I don't remember ever seeing an asymmetry that you might expect from this, but that could be because this is too far out where the field is weaker.
Yes.
But I know that they fit those. I think they do a kind of multipole expansion type thing and fit the curve based on viewing angle and everything to pull out coefficients. And it seems like you could do a similar thing to see if this would be observable.
Yeah, that's a very good point. And also you're right. And this flux tubes actually extend to much longer, like outside 100 RJ. And remember that our simulation does not include a hot population. So the real one, if it's close, it could be even further out. So that's a factor to consider. But definitely, if there's something we can calculate, I'll be happy to do to see if we can derive some more from these simulations.
Yeah, it might be worth just getting in touch with some of the people who do that work, like Scott Bolton or Imke Potter, to see, how they do that kind of simulation or fitting and see if you could generate something. I think you'd have to assume something about the particle distributions as well and what the emission was. And anyway, thank you.
Great.
Do we have more comments or questions to any of the speakers?
I have a question for the second speaker on the modeling and the rotation. The simulations are being compared to a Dungy type model for Jupiter's magnetosphere. And sometimes when you read the literature, there's a second kind of model that discusses the configuration of Jupiter's magnetosphere and where reconnection occurs and how it occurs. And that's the Vaseline model. And so could you say something about like whether the experts still believe the Vaseline model and how it compares to these two other kind of viewpoints?
Okay, so the Vaseline model, which talks more about where the flux circulates in the tail. So if you look at the simulation results, and the Vaseline cycle is actually included in the simulation. So you can see these are where in the tail that we have this reconnection across the dawn dusk and generated by, maybe this is clear. So it doesn't tell us how much the dayside merging is impacting. So this, our results more focus on the dayside merging on the polar region of the flux circulation rather than the tail. So, but the Vaseline model is, I think it's included in this simulation, and how much it's doing it, and there are lots of details and haven't looked, but that's definitely something we're going to look in the future.
I have a second question, and that goes back
Sure.
to your reconnection parameters, where you use Faraday's law basically to figure out, and so you get a reconnection, you get the reconnection potential or the reconnection EMF, and you multiply by delta T.
Yeah.
And so delta T is the time scale for a flux tube to convect over the magnetosphere from the day side to the night side. And within a conventional picture, that's kind of a period for the reconnection rates to be unbalanced, right? That's how long it takes to initiate reconnection on the tail side, the flux tube. And so that's a picture that evolved with the Earth's magnetosphere. But there's a second picture there too, as to maybe what did I get that right? Is that the way you're interpreting your delta T there?
Yeah, so yes. So if you just look at this equation, right? So if you just look at the Faraday's law, and there's actually, this is increasing with time. So the assumption is that if we run the simulation longer enough, so any open flux created down here, and it's actually leaving the system and closed through the tail. So there's like a dynamic balance between the day side and night side. So the time difference between these, the first flux tube and last flux tube leaving the system, I'm calling this delta T. And this is just a very rough estimation. There are other things because night side situation is more complicated. So we get a estimation about 24 gig Weber, and compared to the actual field line tracing, and that gives about this picture gives about 28 gig Weber. So the estimation is actually not that bad, but there is about like 10-20% difference.
I see. So you can actually take that assumption and you can test it with your simulation, and so it makes sense in that context.
Yeah, so this is like the first estimation based on just how this the large scale picture is looking at, and the actual field line tracing with the fields, and we did, and that's actually consistent with what that simple model is. But you're right, it's definitely more complicated.
So yeah, I was thinking like of a second mechanism that equilibrates the day side and the night side reconnection rates, that operates much faster. And this flows from a paper by Corniti, I think he's the first author, in which the demand for the demand for flux at the day side launches a rarefractive wave, fast mode rarefractive wave throughout the entire magnetosphere. And this propagates backwards and shoves magnetic flux towards the day side, and it reaches the night side, and where it equilibrates. And that doesn't operate on convection timescales. It operates on fast mode propagation timescales. So that would be much faster. And it would be, and so it's just a thought. It's an extra thing that could be going on.
Okay, yeah, I get your point. Yes, I think I get your point. And I think in this estimation, it's kind of like, because the X line is actually shorter than the traveling time of the flux tubes. So that's kind of like making this this information that these actually travels. No, I think no, I take it back. It's the opposite. All right, sorry about that. All right, okay. So if it's shorter, then the flux should be even smaller. Is that what you're saying?
Yeah, I just think that it's an extra thing that you might want to think about.
Okay, great, got it. Okay.
Yeah, that and it's not clear to me. Does your simulation operate on fast enough timescales to support like propagation of fast mode waves through the system?
Yes, we do. We do resolve fast wave because it's the ideal MHD. So we do have fast waves.
I see, and your time steps and all that stuff are good too. For
yes.
That.
Yeah.
Okay, good. Okay, great. Thanks a lot. Very nice talk.
Sure. Thanks.
More comments or questions online? George, it looks like you have some comments that you're putting in the chat. If you'd like to voice them, you're welcome to.
Oh, Robin and I were just discussing the synchrotron emissions, and I just, the last thing I said is Daniel Santos Costa seems to be kind of one of the leading experts that still actively publishes using like LOFAR and VLA and stuff. And so we should reach out to him. It'd be, keep our minds open, and it would be really cool if we could do something like that.
But along the same lines, I was going to ask this question to both speakers, actually, in the sense that synchrotron observations, of course, something that we can make here from Earth, but we have Juno there now, and hopefully we'll have Compass in the near future. So looking at the interesting features associated with the magnetic field configuration that Bin was talking about, there are probably some in situ signatures that we can be looking for, such as strong currents from one hemisphere to another hemisphere, that we can perhaps start looking at now we're using Juno data, and then think about what can we build on for the upcoming missions to.
So Sasha, if I could quickly plug Juno's extended mission, we were very aware of Bin's results and excited about those possibilities. So Juno is now at extreme southern latitudes, and Bill Kurth, actually I see is on the line. He recently found evidence of maybe Juno is seeing signatures of magnetopause boundaries and stuff again. So I think this is an active area of research moving forward, and Juno will be able to test some of these ideas, looking for open flux. And we also are going to be flying at very low altitudes and trying to understand, at least anyway, some of the acceleration consequences in the Northern Hemisphere. So,
well, George,
I see Bill unmuted.
George, since you used my name in vain,
sorry.
I'll just make a comment about the synchrotron question that Robin raised. The synchrotron emission at Jupiter, as far as I understand, is the only planet in the solar system that actually has synchrotron radiation, and it's limited to the extremely high energy particles. And typically, these are on very small L shells or M shells, that is field lines that do not extend very far from the planet. And I am not aware of any observations from the VLA or from Cassini or Juno that suggest that there are synchrotron emissions coming from these field lines that exit the polar cap. Now, you might ask if some of the lower frequency emissions, like the decametric or hectometric emissions, are associated with those field lines. And I think the jury's still out on that, but there's a fairly nice study that Krent and Lewis did that showed that if you do direction finding on radio emissions coming from Jupiter's auroras, they tend to be located on field lines that thread the main auroral oval. I'm not aware of results that show radio emissions coming from those field lines that are in the so-called swirl region. I could be out of date, but I think that's what I recall.
Thank you, Bill. More comments or questions online to either of the speakers? If not, I would like to thank them both very, very much for putting together fantastic presentations to start us off. A very good start, I must add to that. And I would like to thank everybody else for diving in. We will announce our next seminar in 4 weeks separately in terms of topics, but this will be both via various emails and newsletters, and it will appear on this new website that we're putting together. So, and with that, I would like to wish our folks in Asia good night, and folks on the West Coast finish your Friday morning well, and have a good day. And with that, thank you all, and have a great weekend.
Thank you. Take care.
Bye.
Bye.